Today we're going to be looking at another heavily requested NileRed video. Specifically this one here, making aerogel.
We're getting really interested in aerogel, which is one of the lightest known materials. There are many different types of aerogel, but the most common one is from silica, and that's what I have here. By volume though, it's actually less than 1% silica, and over 99% of it is just air.
Aerogel is often thought of as a crazy insulator, and it can be used in applications such as spacecraft, sensors, acoustic dampening, and even some nuclear applications as well.
This makes it extremely light, and when I'm holding it, I can almost barely tell that it's there. There are many potential uses for silica aerogel, but its simplest and probably most common use is as a thermal insulator. This is because it's mostly made of air, which in general is a good insulator, but the key part is that all this air is trapped in a network of silica. This makes it really hard for the air molecules to move around and for the heat to transfer to the other side. On the surface, the general process was relatively simple, where all I had to do was make an alcohol-based gel and then dry it. However, the issue is that in practice, it's way more difficult, and getting even a decent quality aerogel is really hard. I wasn't looking for anything fancy though, and I wanted it to be as easy as possible, and it seemed like a recipe from aerogel.org fit that perfectly.
Aerogel.org?
The first chemical that I needed for it was the hardest to get, and it was something called tetramethyl orthosilicate, or TMOS for short. This is basically a liquid source of silica, and because of that, it's also really dangerous. Now, the other things that I needed were methanol and concentrated ammonia. For the methanol, I just bought it from a local hardware store, and I got the ammonia online. With all the ingredients, I was now ready to get started, and the first thing that I had to do was make some dilute ammonia.
I like that you can make all this with household ingredients. The stuff that I had here
was concentrated, so it was around 28 to 30%, but I needed it to be closer to around 0.1 or 0.2. To do this, I just added 5.4 mils of the concentrated stuff to a bottle and poured in a liter of distilled water. After this, I moved on to making the actual gel solution, and I added 33 mils of methanol to 2 beakers, and then into the one on the left, I also added 16.5 mils of that dilute ammonia that I just made.
One of the methods for raising power in a pressurized water reactor is simply diluting the water, because the water contains boric acid. Think liquid control rods, because the boron absorbs neutrons and slows down the fission reaction. So by diluting it, you're removing some of it, and that is a way to raise power. And you do this routinely over the course of a fuel cycle. As the fuel gets burned up, the uranium fuel does, you dilute the reactor-grade water, which has boric acid in solution, in order to maintain power at 100%. To give you a sense, at the beginning of life, we start off at around 1,400 parts per million boric acid, and we end with less than 30. What's interesting is for a reactor operator, simply looking at your boric acid concentration is one of the fastest ways to tell where you are in core life.
With this all added, I then busted out the TMOS, and I carefully poured in 33 mils to the one on the right. This gave me my 2 starting solutions, and to make the gel, all I had to do was mix them. During this phase, which was what I had here, it was still completely liquid. As more of it formed though, the particles would come together and form a complicated and fragile network of silica. The major goal of this project was to make aerogel in general, but I also wanted it to be as beautiful as possible. The ones that you can buy are always these nice cubes or well-defined shapes, and I wanted to get as close to that as I could. So I had to somehow come up with a way to do this, and this was the part that made making the gels a lot harder than I initially thought.
Nice smooth surface.
This is mostly because the final gels are really delicate, to the point that I feel like they could break almost just by looking at them.
That is one of the biggest disadvantages of aerogel, is the brittle failure mechanism. And you could potentially use something like this in a nuclear power plant, because dealing with very high temperatures, very high pressures, and a good thermal insulator is what you need. Problem is, in addition just to the cost of manufacturing, There's also a type of brittle failure, and if it were to shatter in an operating nuclear power plant where you suddenly lose your a lot of your good heat insulation, that can just be a problem with any large industrial pressure vessel. So that's one of the reasons why you're not going to see it. Brittle fracture considerations are used post-accident when evaluating the status of the reactor. And the biggest vulnerability to causing brittle fracture would be a rapid cool down and sudden repressurization. That's one of the reasons why cool down rates are limited in a nuclear power plant, just for a regular cool down. And post-accident, there are actually situations where you would turn off your high-pressure emergency core cooling pumps just because the pressure would be too great and you risk fracturing the vessel. So instead, you use just your low-pressure coolant injection pumps. The reason why you have both is you could potentially have a loss of coolant accident while the reactor is still highly pressurized, and you need that high pressure just to move the water into the reactor vessel. Otherwise, the back pressure would just keep you out. So that's one of the reasons why you have both. Another reason why you're not going to see aerogel in a nuclear power plant is it doesn't do anything for you in terms of radiation shielding, since, like NileRed said, it's 99% air, and air will eventually slow down certain types of radiation, but it's would be the equivalent of using really expensive air, and it would really it's really designed for heat transfer purposes. So it's compared to concrete or lead, it's not going to have any of the radiation stopping power that you would see. Oh yeah, you could breathe on it.
This totally ruled out using any of those soft silicone molds, and it
looks like an ice tray.
Would just get stuck in any hard mold. So, I wasn't able to use any traditional mold for this, and I had to get a bit creative. I spent about a week trying out random things, and eventually, I came up with something that worked. It was also really cheap and easy, and what I ended up using was a plastic cookie cutter that I got from Amazon. I think it might have been okay on its own,
awesome.
But to make sure that the gel didn't stick to it, I sprayed it with a bunch of silicone lubricant and wiped it down. After that, I put it onto a piece of glass that I took out of my IKEA display cabinet, and I made a border around it with duct tape. With the tape in place, I took away the cookie cutter, and I used a dollar store cheese grater to shred one whole dollar store candle.
There's an old engineering joke that, like 90% of engineering solutions, if you want something to not move, use duct tape. If you want something to move, use WD-40.
I then melted all the wax by blasting it with my heat gun, which is basically an overpowered hairdryer.
Yeah.
When it all seemed nice and
cool.
liquidy, I used a ruler to scrape off the extra stuff, and the goal
I
was
love
to
that this
make
is
a
all with
layer
household tools.
about the thickness of the tape. This part was always a little bit sloppy, and I usually had to scrape it and remelt it at least a couple times. It didn't have to be perfect though, and all I wanted was for the glass to be covered in a somewhat even layer of wax. When I felt that I had this, I dropped the cookie cutter onto it, and I put a dish on top to help keep it in place. I then shot it again with the heat gun to really make sure that the edges were sealed, and I let it sit there for 30 minutes for all the wax to harden. I found that the best amount to add was 10.4 mils, and I did this as fast as I could, and then covered the whole thing with a dish. As the reaction continued,
very zen watching him fill those up.
Slowly heat up, and without a cover, the gels would all dry out and crack. With the dish though, the methanol vapor was kept inside, and this problem seemed to be avoided. What I had to do now was basically just wait for it all to turn into a gel. This usually took around 10 or 15 minutes, but just by looking at it, it was very hard to tell when it was ready. So, I came up with a very scientific method to figure this out, where I would occasionally just punch the table and see how it shook.
That's awesome.
I also found that it was just good to punch the table in general, because even early on, it helped release some bubbles.
I thought I was going to say
Eventually,
relieve
around
some
the 10-minute
stress.
mark, when I would hit the table, it looked pretty solid. When I saw
NileRed's
this, I
just
would usually
awesome.
give it a few more minutes, and then I would take off the dish and add some more methanol. This had to be done quickly though, because a lot of the methanol had vaporized and there wasn't much of it left on the surface. Right now, they were all still way too fragile, and if I tried moving them, they would probably crack and fall apart. So I let them sit there for another 10 minutes, which gave more time for the TMOS to react and for the gels to get stronger. The gels were all still technically in the mold,
That's
but there
cool.
was now no bottom and I could easily get them out without damaging them. All I had to do was push on them a bit and they slid out really easily. They were all dropped directly into
Ice
a
cube
bunch
tray.
of fresh methanol and I went back to making some more gels. However, this time, I didn't just use the same mold again, and I instead used a hexagon one.
Thing about hexagons is they're more space efficient than squares. There are actually some nuclear power plant designs where the fuel assemblies are laid in hexagonal shapes. That wasn't the case where I worked. They had the square surface, but you've seen those in some of the more modern advanced designs, such as fast breeder reactors. So they're even looking at spatial layout of the fuel. And there's an entire ergonomics, industrial time motion study about the order of when you load the fuel in and unload it to maximize efficiency. It's quite fascinating. That hexagons just look cool. They're often associated with just with things that look high tech.
When this was eventually ready, I whipped up some more gel solution, and again I added it in the same way. When I started this project, I was really hoping to make gels that were completely smooth, but the surface of this one was a bit rough looking. I wanted to see what would happen if I just tried evaporating the methanol, and I also blew on it a bit to try to speed it up. Within a couple minutes, it had cracked all the way through,
yeah.
and when I tried pushing a bit on it,
So
the
delicate.
whole thing just exploded. The cracking here happened really fast because I was blowing on it, but I wanted to see what would happen if I let it evaporate much slower. Can't just dry the gel in a normal way. It has to be done using a specialized method so that it doesn't collapse on itself. There are a couple ways to do this, but I decided to go with the most common way, which is by supercritical drying using CO2. The general idea behind this
That's an expensive process.
was to first replace all the methanol in the gel with liquid CO2. The liquid CO2 is then heated until it goes supercritical, where it's kind of a mixture between a liquid and a gas.
This is not to be confused with the concept of going supercritical in a nuclear power plant, which is a reactor startup, reactor power going up. Though there are power plants, mainly coal power plants, that do operate in the supercritical region. Basically, you have to get pressure and temperature above a certain point in order to get there. It is possible to do it in a nuclear plant, though. I'll pin a comment down below where I talk a bit more about this. And the short version is, it's possible, just untested. This was actually in my reaction to a Nile Blue video where they go more over the concept of supercritical.
Then from there, it can be converted to just plain CO2 gas. By doing this, we're basically turning a liquid into a gas without having to evaporate it. This makes it possible to completely avoid that problem with capillary action, and the gel shouldn't collapse.
Yeah, it's kind of a way to subvert that whole latent heat transfer mode of vaporization. It's an interesting workaround, but pressurizing and raising temperature to get things to beyond that critical point is the trade-off.
I also got the information on how to do this from aerogel.org. They have a full guide and a complete parts list, and they also have a lot of very useful information
Open source
when it
aerogel.
comes to making aerogel in general. The entire thing also had to be made out of high-pressure stainless steel, which wasn't exactly cheap.
Yes, that is one reason why pressure vessels are a lot more expensive, and especially if you go into crazy stuff like for a nuclear power plant, the reactor coolant system piping and all interfaces have to be ASME Class 1 means the highest level of pressure, stress testing, QA, QC review processes. Only the best for nuclear, right?
Fortunately, there wasn't much of a way around this because building it with cheaper materials,
Wow.
especially those not rated
That's
for
an
high
expense.
pressures, is a major safety problem. It all arrived a few days later, and the first thing that I did was take everything out of its packaging and roughly lay it all out. A bigger chamber meant a bigger window, and to me, that probably meant better footage. Each of these windows were unfortunately expensive, and they cost about $400 US.
I appreciate all the investment that NileRed has put into this. One, just being able to make the aerogel, but also really cool footage of the process. This is amazing.
I started by opening the tank, which let out liquid CO2, and it filled the hosing. I then opened the valve on the chamber, and the CO2 started rushing in. The pressure gauge also increased, and I let it max out at around 900 psi before closing it. To empty the chamber, I closed the CO2 tank, reopened the main valve, and then slowly turned the one at the bottom. There was still a small amount of bubbling in some places, and to fix this, I just tightened it a bit more. After that, I tested its holding power by filling it with a bunch of liquid CO2.
Anything involving like reactor grade pressure systems, any fittings, they're specified torque ratings that you need like an engineering review if you want to adjust it. And just the whole tight but not too tight thing is taken to such a critical degree on a system like that. It's fascinating.
Leaving it for a couple days. I marked the height that it started at, and when I came back, it was only a bit lower. I decided to make a bent version of those things that they use to load pizzas into an oven.
That is awesome.
To make this, I just took a random piece of metal that I had lying around, and I hammered it into the rough shape that I wanted. I then used an angle grinder to shape it even more, and I finished it up on a grinding wheel. This was the final result, and it wasn't perfect, but it was honestly way better than I thought it would be. So, I started by filling the chamber with 45 mils of methanol, and I pulled out one of the gels. I then carefully lowered it in, and I made sure that there was enough methanol to completely cover it. I then opened the main tank, and I carefully turned the valve so the liquid CO2 would only trickle in. The goal here was to fill it really slowly over the course of about an hour. One of the biggest factors when it came to making crack-free aerogel seemed to be speed, where slower was almost always better. This was the main reason why I was adding the liquid CO2 over the course of an hour. It can be a bit hard to tell here, but there are two layers where the liquid CO2 is sitting on top of the methanol. To make it more clear, I went ahead and shook it a bit, but this probably wasn't the best for the gel. For the most part, besides when I shook things, these two solvents were completely separated, and they were only slowly mixing together. All I had to do was open the valve at the bottom of the chamber. This again had to be done really slowly, and the target was to do it in about 2.5 hours.
Oh, look at that.
When I stopped seeing methanol dripping out, the CO2 in the chamber was just above the gel, and I closed the valve. When I was done, I checked how much methanol I had, and it was about 40 mils. I started with 45 mils though, so there was still some methanol mixed in with the CO2 in the chamber. The basic goal here was to keep repeating this process over and over until I didn't see anything in the beaker, and then to do it one last time. Now, to supercritically dry the gel, the general idea was really simple. Almost all I had to do was heat it up and push the liquid CO2 into the supercritical state. With CO2, this thankfully happened at a low temperature, and it was barely above room temperature at around 31 C. For this part, I used a heat gun.
To give you a sense, it's 374 degrees Celsius for water and 22 megapascals.
And I carefully blasted the chamber. Almost all of the heat was focused on the largest section, and a small amount was on the small cross. For safety reasons, it was important not to heat any of the valves. The main goal here was to get to 31 C, but as it got hotter, the pressure also increased. I had to make sure that by the time it got to 31 C, that the pressure was just below 1100 psi. I still had to heat it a lot more and push the CO2 further into the supercritical region. This had to be done extremely slowly and carefully by only raising it by a few degrees and then waiting 20 or 30 minutes. As the pressure decreased, all the CO2 in the chamber gradually moved out of the supercritical area.
And that was the whole reason why he had to move it further to the right in terms of temperature, because it's going to go down both in terms of pressure and temperature when he opens that valve. And you don't want to inadvertently cross below the critical point. If that were to occur, you'd basically lose the benefit of going just from supercritical to gas. You don't want to like transition from liquid to gas. That would essentially just defeat the whole purpose of this.
The CO2 though was still quite hot, so instead of turning back into liquid CO2, it was all going back into regular CO2 gas.
Yep.
As a gas, it also has no surface tension, and it should be able to leave the gel without causing any damage. It took an hour and a half to completely depressurize it, and over this time, I had to constantly check on it and adjust the valve.
Yes.
I brought it all over to my vise and unscrewed the window, and now it was time to see if all this work was worth it.
A lot of this actually seemed very similar to how you would fill and vent a heat exchanger before you place it in service at a nuclear power plant or any industrial facility. And the main reason why you do that is just to avoid hydraulic transients, or the term water hammer or fluid hammer. There's all kinds of industry event reports out there about not doing a good, careful fill and vent process, that when you start the system up, you start a large pump and that pressure in, a pipe jumps like 5 feet to the side due to a crazy hydraulic transient. You don't want that.
As I pulled it out, it didn't look like it had shrank or anything, which was definitely a good sign. So at the very least, I had made some sort of aerogel. When I got it out more though, I noticed that there were, unfortunately, at least a few major cracks in it. But despite this, I was still pretty happy with how it turned out. I mean, it wasn't even close to being perfect, but for my first attempt, I thought it was pretty good. This process kind of sucked.
Yes.
It took about 4 days just to prepare the gel in the chamber.
It's one of the reasons why it's so expensive.
An entire day just for the supercritical part. It was also very labor intensive, and I had to babysit it the entire time, and I couldn't really do anything else. Also, on top of this, using a heat gun wasn't really ideal because it was only able to get one side of the chamber.
Yes.
I unfortunately wasn't able to see the gel the whole time, so I don't have a lot of proof of this.
Use omnidirectional heat
It was
guns.
just this supercritical step that really caused the gel to crack. I wanted to try doing it again, but instead of just doing the same thing, I decided to try something new. This time, I didn't use a heat gun, and I instead bought a sous-vide meat cooker. This thing was originally meant to cook things like steak,
Ooh, it looks like a
that it would
lightsaber.
be perfect here. It had a built-in temperature controller,
No, it doesn't.
so all I had to do was put the chamber in the water with it, and then click a button. So to get this started, I loaded the chamber with a hexagon this time, and I repeated the same exchange steps using the liquid CO2. When it was done, I lowered the entire chamber into a tub of water, and I attached the sous vide cooker. I then added as much water as I could, but I was only able to cover half of the main chamber. This was fine though, because the part where the gel was completely covered, as well as a decent portion above it. This would give me good temperature control and consistency in the part that it mattered the most. Even though the upper part wasn't in the water, it would still heat up because the whole thing was made of metal. However,
Sure.
It would also lose a lot of heat to the air, which wasn't good. To try and fix this, I
Cover it in
covered
aluminum
the whole
foil.
thing with aluminum foil, which would help hold an
That's awesome.
insulating pocket of air. The major difference was that I barely had to do anything. I just occasionally
nice.
clicked on the cooker a few times to turn up the temperature, and that was it.
In the previous method, anything where there's a whole program in nuclear power just called operator burdens, where anything where you have to babysit a valve that takes an operator out of their normal job and requires some level of workaround is an operator burden. And one of our regulators actually tracks those and wants to keep those to a minimum, which is great. All the reason to have a robust maintenance system and maintenance decision-making process to prioritize and fix those issues. So it's good to see him find a better way to do this. I really like that. That's one of the things I really like about NileRed is he goes, He shows one way to do it, and then he learns and gets better and shows us that process. That is really, really cool.
What was interesting was that without the camera right against the window, this supercritical part looked a lot different. What was also weird was that at some point, it all turned orange inside the chamber, but there was no orange light anywhere. Then, as it got further past the supercritical point, this color slowly disappeared. As I vented it, I kept looking at the gel, and it looked the same even after all the CO2 was gone.
Okay.
After seeing that, I honestly started to get really excited, but again, it was just a small portion of the gel, and I tried to not get my hopes up too much. I then unscrewed the window, and I took a look inside.
I'm so excited and earnest.
Oh, look at that. And
Don't drop it.
I guess my hopes weren't destroyed. From what I could tell, it was
Beautiful.
completely uncracked, and I could honestly barely believe it. I really did think that this one would be cracked as well, and I thought that it was just going to be a bit less than the last one. What I had here, though, in my opinion, was about as close to perfect as it could have possibly been. I started working on this project back in July, and it has taken a long time to fix all the problems and to get all the supplies.
That is amazing. I really admire the level of dedication to something like this. And it was cool. I got to liked seeing his initial reaction to the success of this project. That is amazing. One potential nuclear application for aerogel is in space travel. This is a fission fragment rocket engine. You use nuclear fission for propulsion in space. You split atoms to produce the fission fragments directly, and when they're expelled at high velocities in a specific direction, they can generate thrust. You would use something like uranium-235 or plutonium-239 as your fuel, very similar to what you see in nuclear power plants on Earth. And you generate heat just like you do on Earth. The heat is then going to be converted into kinetic energy, which is going to be involved. And the working fluid is going to be a gas or a plasma compared to, say, water, what you would have on Earth. And the reason why is liquid water is challenging in space, to say the least, and also a bit of it. You want something light, and you want something that can expand more rapidly. And these fission fragments are accelerated at very high velocities through the nozzle, and it simply generates thrust. Basic third law of motion, the action-reaction principle, and you're going to push your spacecraft forward. It's that simple. This has potential for a high specific impulse, which means high speeds but less overall propellant compared to chemical rockets. One of the biggest challenges with this is managing the extreme heat generated by nuclear fission. And that technical challenge puts it largely in just the theoretical aspect, but it's a highly efficient, highly powerful nuclear fuel. Being energy dense means you can have this engine last a very long time, at least compared to chemical rockets, and at a fraction of the weight, which, considering how expensive it is to get stuff into space, would be a fraction of the cost. So embracing these in an aerogel mix to have that benefit of the ultra-high heat resistance would help, combined with superconducting technology to have magnets to constrain the fission fragment trajectories in order to have it go in that one direction. This would also further aid in miniaturization, since you're not going to have fission fragments go in a direction other than the direction that you would like the thrust. Fission fragments are charged. They're positively charged. That's why the magnet is so helpful in this case. So yes, aerogels and superconductors to make a nuclear-powered rocket engine for interplanetary travel. This is an example of what this amazing technology could be used for. By the way, I'll also include in that pinned comment my reaction to NileRed's video on making superconductors. So you can kind of see both halves You can see my take on both halves of making a really cool piece of technology like this. It's very exciting.
I was extremely lucky that it worked after just 2 real attempts, but it took months and months of constantly reading stuff and trying little things. I was really happy with the final result, and the only issue that I saw were some small bubbles in it, but those were from when I made the original gel. I didn't think they'd be visible in the final Aerogel, but I mean, they obviously were. In the future, I might try to fix that, and I also might try to modify the chamber so that I can load more gels. In my opinion, even with the sous-vide cooker, it was still way too much work just to dry 1.
Yes.
And I'm convinced there's a way to do up to 4.
Aerogel factory.
However, for now, I'm a bit tired of thinking and working on Aerogel, and that probably won't happen for another year.
That was such a fascinating video. Thank you so much for the recommendation of this. And I like seeing things with exotic material with some really cool potential applications. Thank you very much for watching. I'll see you next time.